Creating realistic human image animation is a challenging task. Existing methods, particularly those using the reference to video, or R2V, paradigm, often struggle with a critical problem: identity drift. R2V models use a reference image and a driving video to animate the subject. However, subtle spatiotemporal misalignments between the reference and the driving video accumulate over time. This leads to the generated video deviating from the original subject's appearance, resulting in visual artifacts and a loss of identity. The key insight behind SteadyDancer is to shift from the R2V to the image to video, or I2V, paradigm. Instead of relying on a potentially noisy driving video, SteadyDancer uses only the first frame, the source image, and a sequence of poses to guide the animation. This inherently enforces strong first-frame preservation, ensuring that the generated video stays true to the original identity. The challenge then becomes how to effectively translate pose information into coherent and realistic motion while maintaining the character's original appearance. SteadyDancer tackles the I2V challenge with three core innovations. First, the condition reconciliation mechanism harmonizes conflicting conditions at multiple levels. This involves balancing appearance preservation from the source image with the precise motion dictated by the poses. It uses techniques like fusion, injection, and augmentation to manage these competing signals. Second, synergistic pose modulation modules generate adaptive and coherent pose representations. This includes a spatial structure adaptive refiner to refine pose information based on the source image's spatial structure, a temporal motion coherence module to ensure smooth transitions between frames, and a frame-wise attention alignment unit to align pose features with the source image features. Finally, the staged decoupled objective training pipeline optimizes the model in 3 stages: action supervision to learn basic motion, condition decoupled distillation to improve visual quality, and motion discontinuity mitigation to enhance temporal coherence. Let's examine the condition reconciliation and pose modulation aspects in more detail. The condition reconciliation mechanism uses techniques such as adaptive instance normalization and attention mechanisms to selectively incorporate the appearance information from the source image into the pose-guided feature maps. This ensures that the generated video retains the stylistic elements of the input image. The synergistic pose modulation modules learn to extract pose-conditioned features. The spatial structure adaptive refiner uses convolutional layers with learnable kernels to spatially adapt the pose representation to the structure of the initial image. The temporal motion coherence module leverages recurrent neural networks, RNNs, or transformers to model the temporal dependencies between poses, ensuring smooth and consistent motion. The frame-wise attention alignment unit uses attention mechanisms to align the pose features with the visual features extracted from the source image, improving the accuracy and realism of the animation. SteadyDancer achieves state-of-the-art performance in human image animation. Quantitatively, it demonstrates improved metrics for both appearance fidelity and motion accuracy compared to existing methods. Qualitatively, the generated videos exhibit significantly reduced identity drift and fewer visual artifacts. Importantly, SteadyDancer achieves these results while requiring significantly fewer training resources than comparable approaches. This has important implications for the field, making high-quality human image animation more accessible and efficient. By focusing on the I2V paradigm and developing innovative architectural components, SteadyDancer represents a significant step forward in creating realistic and controllable human animations.